Dear students, now in this PowerPoint slide we have seen shielding and deshielding, nuclear Overhauser effect, spin-spin coupling in NMR spectroscopy. Contents of this PowerPoint slides: first content shielding and deshielding, second content nuclear Overhauser effect which is also called as NOE, shift reagents or chemical shift reagents, spin-spin coupling which is also called as spin-spin splitting. Then next content rules for spin-spin coupling, and last content coupling constant. Firstly, we have seen first content in this PowerPoint slide is shielding and deshielding. All the phenomena mentioned earlier in this chapter were with respect to the nucleus considers to be stripped off from electron, but nucleus surrounded by the electron and hence protons can be present within or outside the circulating magnetic field caused by circulation of electrons in double bond, triple bond, aromatic or other ring systems. When a proton is present inside such magnetic field or closer to an electropositive atom, more applied magnetic field is required to cause excitation. Such protons are called as shielded protons. This effect is called as shielding effect. When a proton is present outside such circulating magnetic field or when it is attached to an electronegative atom, less applied magnetic field is sufficient for excitation. Such protons are called as deshielded protons, and this effect is called as deshielding effect. Now we have seen nuclear Overhauser effect, which is called as NOE. Magnetic nuclei also interact through space, but it does not lead to coupling. The interaction is seen when one of the nuclei is irradiated at its resonance frequency. Then the other is detected as an intenser or weaker signal than usual or normal signal. This is known as NOE, means nuclear Overhauser effect. This effect is seen over short distance, that is 2 to 4 Armstrong unit, between two nuclei. The interaction is dependent upon the relaxation of the observed nucleus by the irradiated nucleus. The nuclear Overhauser effect shows molecular geometry. It tells us whether the two protons are in close proximity within the molecule or not. Line intensities observed in the normal spectrum may not be the same as in the decoupled spectrum. Now we have seen next content, that is shift reagents, which is also called as chemical shift reagents. Lanthanide series of elements are used as shift reagents. A lanthanide ion can increase its coordination number by interacting with unshared electrons. As a result of NMR spectrum of the compound that contains a group possessing unshared pair of electron undergoes change and large chemical shift as a difference in peaks is observed. All the shift reagents are mild Lewis acids. Shift reagents separates NMR signals. Those normally overlap. Thus, it gives more simplified spectrum. The commonly used reagent is dipivalomethanto complex of europium, which is also called EU DPM3. Next reagent is parasmodium, which is PRDPO3. These reagents are beta dicarbonyl complexes of rare earth metals, for example, N-hexane shows peak in slightly upfilled region for methyl and one downfilled peak triplet for hydroxide, and it shows number of peaks for all methylene in the region 1.2 to 1.7. But when shift reagent is added, the spectrum resolves over 1 to 11 delta and is more simple. Shift reagents are paramagnetic, so large chemical shift takes place. The shift is downfilled with EU means europium and upfilled with plasmodium complexes. Broadening of the peaks occurs due to rapid spin lattice relaxation and depends on temperature. At a lower temperature, as there is more relaxation, more is the broadening. Shift reagent is normally used in nonpolar solvents like carbon trichloride, carbon tetrachloride, carbon disulfide, and DMSO. Now we have seen next concept, spin-spin coupling, which is also called as spin-spin splitting. On observing the NMR spectra of compounds, it is seen that the signals are split into number of lines. For example, ethanol, in which ethanol CH3 CH2 OH, the signals given are singlet for OH, quartet for CH2, triplet for CH3. We say that each signal will split into doublet, triplet and quartet depending on the number of protons present on adjacent carbons. The multiplicity of lines is related to the number of protons on neighboring groups. A simple rule, which is also called as n plus 1 rule, is used to find out the multiplicity. Count the number of neighboring protons and add 1. Splitting of the spectral lines arises because of coupling interaction between neighbor protons and is related to the number of possible spin orientations that these neighbors can adopt. This phenomena is called either spin-spin splitting or spin-spin coupling. Now we have seen rules for spin-spin coupling or spin-spin splitting. In general, the following set of rules may be found very helpful in predicting or interpreting the splitting of proton signals. First rule is splitting of a proton signal is caused only by neighboring or vicinal protons. Second rule, splitting of one proton by another on the same carbon very rarely comes across because such protons are generally equivalent each to other. Third rule, the number of peaks into which a proton signal is split up is equal to one more than the number of vicinal protons. And fourth rule, all the peaks of a given multiplet, that is doublet, triplet, quartet, are not of exactly the same intensity. It has been observed that the inner peaks, that is the peaks nearer to the other coupled multiplets, are larger than outer peaks. Now we have seen coupling constant. The distance between the peaks in a given multiplet is a measure of the magnitude of splitting effect. It is referred to as coupling constant and is denoted by the symbol capital J. Numerical value of J is expressed in Hertz or CPS. Unlike the chemical shifts, the values of J are independent of the applied field strength and depend only upon the molecular structure. For a pair of mutually coupled protons, the coupling constant due to splitting by one proton has the same value as the coupling constant due to the splitting by the second proton. In other words, mutually coupled protons show the same magnitude of splitting of each other's signals. In general, the size of coupling constant is determined by the number and kind of intervening chemical bonds and the spatial relations between the protons. For protons attached to the same carbon atom, that is geminal protons, the value of J varies from 0 to 20 Hz depending upon the bond angle and overall structure of the molecule. Second, for protons attached to adjacent carbon atoms, that is vicinal protons, J varies from 2 to 18 Hz depending upon the spatial positions of protons and the structure of the molecule as a whole. So, coupling constants are measure of the effectiveness of spin-spin coupling and have been very useful in getting exact information from PMR spectra of complex molecular structure. Thank you.